So this is an argument that was developed in the context of studying the life sciences. It was done here at Stanford, at Harvard, MIT, down at UC San Diego. So universities played a really important role in the evolution of the life sciences. But I don't think the argument is unique at all to the field of life sciences. I've had students and former students study the development of nanotechnology in the 1980s and 90s using these ideas, the development of electronic computer-mediated music, which started here at CREMA in the 1960s, and also work on the software industry in the US in the 60s and 70s. So a special case study, I'll try to give you some generalization, but I think the general argument is quite broad. Feel free, it's a little, I feel like a very tall person up here, but if you have questions along the way, just pop your hand up, okay? So this shouldn't be me talking at you. What's unique, I think, in some respects about this work is we try to think about why do things develop at particular points in history, and why do they happen in particular places? So to think about that, you have to think about history. You have to think about stages or sequences of development. People always tell you, oh, you should have been here yesterday, or it's not like it was 15 years ago, or not like it was 10 years ago. And we also want to know about space. Why are some places more innovative, let us call it, than other places? Why do places with the same combination of resources not develop the way that others do? Now, that sounds like an important question. It actually turns out to be a really hard question to study, because most of the time the origins of things are pretty opaque. The economist Peyton Young says most social science and most management research starts after the dust is settled. It never asks where the dust came from, okay? And so what we want to try to do is push back on that and think about ways that you could study it. If you read most of the literature, it usually says, looking at successful cases, the following things happen. But when you only sample on the dependent variable, when you only look at success, you tell very unusual kinds of stories. Usually you say somebody invented something, somebody had a problem to solve, somebody was more successful at something. So what we try to do is start at the beginning, before a field emerged, and try to understand why something happened in only a few places as opposed to a large number. Okay? So this is a map way back in 1978, the dawn of the life sciences. You can argue that this is just about the beginning. The science of gene splicing, the first paper was published here and at UCSF in 1972. The initial work on mice was done in 1973, 1974. One of the first companies, Genentech, was founded in 1976. So this is a map of where the 30 first companies were in 1978. The size of nodes, of circles, reflects the number of companies in a region. So when you see this map, what do you see? What do you see? East Coast, West Coast, okay, yes? There's a Bowash corridor, so somewhere between Washington, Philadelphia, Princeton, New Jersey, New York, Boston, something's going on, and then there's a West Coast. Save for Cincinnati and Memphis and Houston and Dallas, the Midwest looks like Portuguese explorers' maps of Africa in the 16th century. There dwelleth lions in the hinterland. Not a whole lot going on in the middle of the country in this. Miami, Florida is an interesting one. The Research Triangle, Washington, D.C. So there's a variety of different possibilities, okay? So there are a lot of candidates for where clusters might be formed. So we go back in the data to 1980 and collect the number of biomedical patents in urban areas across the United States, all right? So you might argue that biomedical patents are the intellectual property rights that would be needed to create an industry. And then we rank them. Turns out New York City and northern New Jersey are the most active places. New York has an amazing array, world's leading array of research hospitals. Sloan Kettering is one of the leaders, but there are many others. Lots of elite universities, NYU, Columbia, Cornell's medical school is in New York, and it's where the money is. It's where investment banks are. So it would seem to be a very good candidate, okay? Also, biotech was a clean industry, no smokestacks, didn't need big spaces. Northern New Jersey is actually the home to the US pharmaceutical industry. It's where Merck and Johnson & Johnson are located, but it's also where many of the German and Swiss companies were located. Philadelphia historically was the cradle of pharmacy in the US. It's where the chemical industry was. It's where the biochem industry developed. Princeton, New Jersey is not far away. Princeton University is not that far away. You would think Philly, New York City would be a leading cluster. There's also University of Pennsylvania and the Fox Chase Cancer Center. So lots of possibilities for Penn. The Bay Area had UC San Francisco and Stanford, so certainly some strength. Berkeley didn't have a medical school, but has biochemical engineering. But maybe there's crowding from the information and computer technology industries. Boston seems an obvious case. MIT, you would say Harvard, although back until 1993, Harvard did not allow its faculty to be involved in the commercial development of industry. Derek Bach thought somehow commerce and science were at odds with one another. And it may seem like a quaint thought in today's world, but it actually was a big feature in Boston. But lots of research institutes in Boston as well. So many possibilities in Boston. Washington, D.C., one of the most obvious places. That's where the NIH is. The NIH's budget is around $30 billion a year for biomedical research. Johns Hopkins is the largest, most successful medical school in the country. Seems like an important candidate. LA has 3 major universities. It also had one of the very first biotech firms, Amgen. North Carolina, the governor, the universities put all kinds of money into building a research triangle. I could go on. You see, there are a lot of possible candidates. Way down the list is a sleepy tourist town, a Navy town. Great town for surfing. I grew up there, San Diego, or at least teenage years. But no one would have ever imagined San Diego as a biomedical cluster. Although it did have these funny places, actually right at one of the better surf spots, Scripps. Scripps Institute, Salk Institute, and the Burnham Institute, these nonprofit institutes. All right, well, let's fast forward and go to 2012. The industry's expanded tenfold, more than tenfold. What do you see now? Bigger bubble. You see bigger bubbles in 3 places. Boston, the Bay Area, and San Diego. What else do you see? It's spread across the country. Salt Lake City, what the heck is going on in Salt Lake City? What do you usually associate with Salt Lake City, Utah? Mormons. Who said Mormons? All right. What do Mormons and Iceland have in common? Genealogy. So Iceland and Salt Lake City are the centers of the world's genomics industry because they track the genealogy of their citizens, their residents, and that turns out to be incredibly useful. So there are ways that you can make a cluster happen based on local resources, all right? And so that the Mormon database and the Icelandic database, very important. So you can see the industry spreads around the country, but nobody gets large save for these 3 places. And that Boston-Washington corridor ends up being a Boston corridor. Not so much changes in New York, New Jersey, Philadelphia, Washington, D.C., Raleigh, Durham. Now, just because you're in one of these clusters, I'm going to stress this later, but I want to go ahead and say now, doesn't mean that you're going to be successful. In fact, you'll soon see that there are very high rates of disbandings, I want to call them. I don't want to call them failures in many of these clusters. The turnover is very high. And in lots of these other areas, university towns in particular, you see possibilities. But something happened, and that something, we call it, is agglomeration or geographic propinquity. So what happened is, even though the leading sources of knowledge and expertise were spread all over the US and all over the world, if I did this map of the world, you'd find similar concentration around Cambridge, UK, even though places like the Institut Chimie in Strasbourg or other centers, the Karolinska in Stockholm, are some of the best research places in the world, no clusters developed there. All right, so there are lots of places with endowments, but only a few took off. And by 2000, and it's even more concentrated today, nearly 50% of the employment, the pills, the patents, the publications come out of just 3 areas, all right? And so that's what we want to try to understand today, what we call geographic propinquity, a feature of emergence that's not anticipated at the beginning, all right? There's no bet. I tried to show you, if you were a betting person, you would not have bet on San Diego, okay? But it becomes self-reinforcing, okay? So what the heck is self-reinforcing? And by self-reinforcing, I want to talk about an endogenous process in which people get attracted to a particular idea, common expectations get formed, so people act in a particular way. Those norms guide their interactions, and then legacies get formed that are sustained by shared cognitive beliefs, all right? That was a mouthful, but that's the process we want to capture: emergence, geographic propinquity, and the self-reinforcing process. Okay, so why does this happen? What is it about places that are successful as opposed to places that are unsuccessful? I'll give you the punchline now and then walk you through the illustrations, okay? So one feature of the places that are successful, we can post the slides, so don't worry about making sure you have great pictures, is a diversity of organizational forms. Now, what do I mean by form? In a very simple way, let's imagine public, private, and nonprofit as 3 different kinds of forms. They play by different rules. Private sector plays by market rules. Public sector pays attention to voters. Nonprofit sector is oriented towards social purpose. So that mix of forms is consequential because the mix of forms means that they have different criteria for evaluating success. That makes possible the ideas can move from one form to another. And that's what I'm going to call transposition. All right, so I'm going to give you some examples of transposition in a minute that are kind of easy to get a sense on. The other feature that turns out to be really important in the successful clusters is there's what we call an anchor tenant. How many people know the idea of anchor tenant from real estate? Okay. Shopping mall has a big store. That means little stores can be there. The little stores provide the variety. The big store provides the foot traffic, and they all benefit from a similar thing. I want to talk about an anchor in a little bit differently. I want the same catalytic action to flow out of the anchor. But I also want to talk about an anchor that maintains the values of a community and makes possible open transfer of ideas. That turns out to be really important. So it's not just a story about diversity, and it's not just a story about connectivity. It's a story about diversity and connectivity allowing ideas to spread across domains so that unexpected things happen, all right? That's the important part, where you get connections, where I usually do this with students. I ask them, if you have you have an apple and you have an apple and you trade apples, how many apples do you have? Okay, if you have an idea and you have an idea and you trade ideas, how many ideas do you have? No. At least 3. She said exponential, so that's right. So 1 and 1 make 2, but the collision of 1 and 1 certainly make possible 3, and maybe, as you said, exponential. So that's the important. The exponential means the ideas have ramifying effects and come back and transform the worlds they came from. All right? Okay, so let me shift for a moment to give you an illustration outside of biotech, because you're going to get a lot about biotech. You might say, oh, this is really specialized to biotech. So I'm going to talk about baseball and politics, really boring things, right? So the idea I want you to have in your head is a contrast between what I call innovation and invention. Innovation I want you to think of as spillover from proximate domains, things adjacent. A biologist, Stuart Kaufman, describes innovation as the adjacent possible. It's like the room next door. When you go, got your living room and your family room and you switch the art around or you change the rugs. It really does remake the feel of a room even without buying anything new. But that's an interstitial process where known things are combined. It improves, sometimes in a dramatic, revolutionary way, on ways of doing things. Invention I want to think about as transposition across distant worlds. You go down the street and swipe your neighbor's art and put it on your couch. It has a very, above your couch, has a very strange feeling. It's not yours. You've engaged in something that's transgressive, but it can really remake that room. So transpositions are often punished. Swiping the neighbor's art might get you in a lot of trouble, okay? So most of the time people want to shut down transpositions, but when it happens, cascades happen and changes the way things are done, all right? So one has a higher rate of success, one has wider ramifications. Let me give you an example. Familiar things here? Well, maybe not to Stanford undergraduates, they're not. Very few have actually seen some of these things, I kid you not, I teach a class where we begin with the Beatles, A Day in the Life, to give them an idea of computer-enhanced music. There are students who ask, who are the Beatles? The world is changing. So we have here a camera, an old-fashioned phone, one of the early Osborne computers, an early TV set. Those all get recombined into something that's now ubiquitous, the phone. But let me try something much more far-fetched, what I might call invention. This is Willie Mays. Many people thought Willie Mays the greatest baseball player of his era, maybe of all time. He could run, hit, throw. He could do everything. This is a famous catch in Game 1 of the World Series, 1954. Someone just did it. Running backwards, not looking, catching it over shoulder, turning around, throwing it back, and doubling up the runner on second. The Giants went on to win the World Series, okay? This is the Black-Scholes pricing model, developed at MIT. I was a young faculty member at the time, and we all were puzzled that Myron Scholes was leaving the faculty to go to Wall Street. And this was a model of how to find underutilized assets. And it was applied to companies. But some people came along and applied it to sports. And the first place it got applied to was baseball. So there's a transgression, a model of finance that becomes utilized in sports. The person who became famous for doing this was a baseball geek, a statistician named Nate Silver. He used to do only baseball, then he started doing football. But then he decided, maybe I could do politics with the same thing. And he predicted back in 2008 an election landslide for Barack Obama. He also predicted that the Tampa Bay Rays would win the World Series. He was a little off. They made it to the World Series, but they didn't get to Game 7. Here's Silver. He runs something called 538 now. When I talk about transposition, what I want to see is how that changed. That is, we've gone from the world of finance to buying players. It then has reverberations back into baseball because they started doing something no one's ever done before. They started playing according to the swings of particular batters and the pitches. And so they started changing the defense. And it was the Tampa Bay Rays that started this, in which no longer having a third baseman for a left-handed batter. Here's an example from the Boston Red Sox, where the young guy from Tampa moved to the Red Sox. And they move a shift when the famous Red Sox player, Big Papi, comes up to bat, and they put the second baseman out in right field, okay? Moneyball spreads back into the university. It's one of the most popular courses at Caltech. In winter 2014, the dean of students, a political science professor, gets together with the director of player development for the Dodgers, who's now a Moneyball fan, and they teach a course on the art and science of Moneyball. And then more recently, I pulled this off the New York Times. It seems quaint today. Words take a backseat to spreadsheets and metrics as more aspects of life become quantifiable and apps track even our moods. It looks as if the nerds have won, okay? Well, not only have they won, in 2014, I don't know if you can see that up there, June 2014, Baseball's Great Experiment, Sports Illustrated, predicted 3 years later that the Houston Astros would win the World Series. Because the Houston Astros were the most data analytic team in the league by then, and signed players on the basis of Moneyball, and signed and organized their team on the basis of Moneyball. Interestingly, the Dodgers are considered the second most analytic team, and that's who they just beat in a 7-game series. All right, so that's an idea of how something from finance at MIT can travel to Wall Street, can travel to baseball, and can actually transform the way baseball is played. That's what I mean by transposition. The baseball story is a simple one because it began with a poor team right here in the Bay Area, the Oakland A's. They had an owner who wouldn't spend any money. And so Billy Beane had to figure out, what's a way I could put a team together? I can find undervalued assets, players who walk a lot, players who don't swing very often so that the pitchers get tired, players that specialize in particular fields. He assembled a cheap team that won 21 games in a row that year. It spread from Oakland to Tampa Bay, so initially it was the poor teams, but then it spread from there to a rich team, the Red Sox, then to the Cubs, then to the Dodgers, and the Astros were the ones all along. But this opened up all kinds of new career options. So guess where PhDs from our economics department and from Berkeley's economics department go now? They go to work in general managers' offices and baseball teams, because what they can do is figure out the value of particular kinds of players, all right? And all kinds of new courses spread at places like Caltech and MIT. Now you have a look on your face like, this is baseball? Yeah, this is baseball. This stats-driven world has really transformed baseball. It's creeping into basketball. One of Beane's proteges has now moved to Ajax in Holland to try to spread this to European football. It's pretty widespread, and of course we know, for better or for worse, how much it was used in the last election by the Trump campaign to figure out particular districts where they should spend money and where they would get the most payback in terms of spending money. All right, let's leave politics, baseball, go back to biotech. All right, let me tell you how we develop the data that tell this story. So we look at the life sciences. We want to look at universities, research institutes, hospitals, small companies, established companies, various kinds of funders, all right? We find a database that covers all these organizations and the formal interorganizational collaborations among the organizations. So we have contract data. It's a little bit left censored. It doesn't quite go all the way back to 1980 because the US government's data was a tad spotty before '88. We build a network of affiliation. So these are the pictures Martha talked about. I don't know how beautiful they are, but I like them, and I'll explain them to you. But the pictures alone are not the whole story. So I was once in Washington, D.C. at a talk at people from the NIH and researchers were speaking to senators and congressmen. what an era that was. You actually sat down and talked with people. And the discussion was about what's the effect of university research on commercial development in the life sciences. And I was sitting there with a fellow, Ed Pinhode, who had been the chair of biochemistry at Berkeley. He went on to be a co-founder of Chiron, one of the first Berkeley or Emeryville-based biotech companies. He later became a dean at UCSF. He became president of the Gordon Moore Foundation. He's a bit of a polymath that has moved through these different places. And he said, Chiron has hundreds of collaborations. I got nervous. I went to the phone before cell phones, called my graduate assistant, who back in the day, you know, was of course chained to the desk, white collar slavery used to be able to have with grad students. She answers the phone. I said, Chiron says they have hundreds of collaborations. How many do they have? She calls me back 10 minutes later. We have 64. So I'm sitting there. Wow, this database really undercounts. What should I do? So I get the nerve up, pick up the phone call. Dr. Pinhode, could I buy you a drink? We go downstairs to a bar. It's a boring Marriott in Bethesda, Maryland. He said, what's up? I said, I'm worried. I'm following the life sciences industry, and we have 64 collaborations for you, and you said you had hundreds. He said, oh, interesting. I will check to how many we have that are involve the lawyers, how many we have under contract. But I say we have several hundred because we have all kinds of probes going on. That is, you know, informal relationships, handshake deals, experimentation, what have you. We'll figure it out, don't worry. Next morning he comes in, hey, I checked. We have 65. We just signed one recently. I'm like, oh boy, the research is okay. Well, what the hell are these other ones? And he said, we actually have rules, we have norms about them. If they, and remember this is 1994, if they involve less than $250,000, we don't get the lawyers involved. If they're less than 3 years in length, we don't get the lawyers involved. And if they're not disputes, potential disputes over patent ownership, we don't get the lawyers involved. If it crosses that threshold, we ask the lawyers to get involved and we make it contractual. So you might think that what we've captured is the tip of an iceberg. And so one of the things we've done is try to get grad students, postdocs, dozens of people who have gone on to make careers of doing field work in university technology licensing offices, spending time in companies, interviewing scientists, interviewing VCs. So I want to stress, what I'm going to show you is kind of tip of an iceberg in which the iceberg, ooh, this is a horrible metaphor with climate change, is, you know, lifting up. What's happening underneath supports this process. I'm going to show you some fancy pictures. They use a visualization technique called Payak. Payak is Slovenian for spider. It's a freeware application. Essentially, it does one thing really well. It's a minimum energy drawing, okay? If you're friends with someone, it pulls you together. If you don't know someone, it pushes you apart, all right? I'll show you a picture in a minute. But I want, before I do that, to ask you, how many of you, you're really a lot of different ages here. How many of you remember high school dances? All right, we got enough. This side of the room, not so much. This side, all right. So what was a typical high school dance? This table here. A prom, but I mean, what's the social structure of a high school dance?
Men on this side, women on this side.
All right, men and women on different sides. Who was in the middle? Dance teacher. My high school, there was a small set of kids who we call the cool kids. They were in the middle, and the rest of us stood around watching them, okay? We didn't form a rival cool kid group. We just stood there like, you know, life was pretty grim, and the cool kids danced. How did you get to the middle?
Cool kid asked.
You had to be asked by another cool kid, all right? That's a dynamic called a cumulative advantage. You might call it the Matthew effect. To them that have, more shall be given, all right? It's a popularity bias. It's one of the most common algorithms you can find. Rich get richer is another way of describing it. So it's sort of a baseline that we ought to watch, okay? Now I'm going to show you some visualizations that run counter to that baseline, and we want to figure out why that's the case. All right, so here's a high school dance in Boston in 1988, except it's not a high school dance. This is the evolution of the biotech community in Boston in 1988. It's only contractual relations among entities in Boston. It's an industry. Life sciences industry, okay? It's the development of the industry. A couple of things you need to know. If you get this picture, we'll cruise for the next 15 minutes. So I have to spend a little time explaining the picture. The circle on the outside, those are the kids not dancing. Those in the middle are the cool kids. The shapes, which I hope you can see, of the dots, circles are dedicated biotech firms. Triangles are what I'm going to call public research organizations. Harvard, MIT, nonprofit research institutes, research hospitals. Squares, which interestingly there are none of in this picture in '88, are venture capital firms. So everybody will tell you, oh, the recipe for development is you need money. Boston didn't have money in 1988. Comes later. Diamonds are big pharmaceutical companies. There aren't any here either. They come later. And then the lines, we call these nodes and edges. The edges are the activity. Research and development is red, finance is green, commercialization, that's downstream, product development is blue, and lavender is licensing, okay? So looking at the big picture, who are the coolest kids at the dance? MIT. What the heck? This is supposed to be a map of the commercial development of an industry. We went back and reran this about 10 times. Like, what the heck is MIT doing in the middle? Harvard is there, even though Derek Bach says it shouldn't be. New England Medical Center, Dana-Farber Cancer Institute. It's all public research organizations. That was a puzzle. So we were playing around with this software. And there's something you can do, which is you can extract the main component. That is, you can take the most connected group, like a main component. Imagine you're doing a friendship network yourself. You put a pin down and you draw your friends. If you ever have to lift the pin up, you've broken the main component. So the main component is a really minimal characterization of what things fit together. You could reach 43% of the biotech firms through this main component. If you took the public research organizations out, the network collapses. Wow, we thought, what a finding. We published this, got lots of attention. I'll show you the next picture. And we thought, oh boy, we got a recipe. This is the story. Public research organizations are the answer to this. Maybe not. But let's go forward 10 years, 1998. What happened to the cool kids? They're not controlling things. Lots more participants come into the dance. They're more inside than outside now, so this is a very growing, capacious place. Harvard is now a very cool kid. MIT continues to be a cool kid. There's some firms that are connected to the two. You extract the main component, and now you can reach 71% of the companies in the area, but you remove the public research organizations now, and the network doesn't fall apart. It's now held up by a second group, the venture capital firms that moved to Boston from Silicon Valley and from New York to get in on the action. And they're the squares and those green lines, okay? So something's going on in which the initial catalysts are super important. They maintain their influential role, but they pass the baton in a way to someone else. So think about the lessons from Boston, and then I'll run through these others. So PROs, local public research organizations, they were really important in getting this cluster started. R&D ties to local PROs increased rates of patenting by the biotech firms. The network shifted to become anchored by for-profits, and ties outside of Boston grew rapidly. So there's something to think about, and I won't go into it today. It's a big topic for economic development. You had to build a local base before you built a national and international base. So there's a sequence to this process. The ties to local PROs receded, but their footprint remained. And what happened is they set the tone for the area. So the way we talked about this is collaboration with universities is like a watering hose with lots of holes in it along the way. There are lots of leaks. There are plenty of spillovers. Academics talk too much. Scientists and firms talk too much to academics, or talk not enough maybe, but ideas flow out pretty easily. Ties between commercial entities are like sewer pipes, concrete. Ideas don't flow out, they just go to the end. So what happened in Boston is that the nature of collaboration was set early by the public research organizations, and they ended up shaping the development of the Boston community. So much so that if today we went to Boston, we would go to Kendall Square, and we'd see that the anchor tenant is no longer MIT, but it's a Swiss company called Novartis. And a Swiss company moved to Kendall Square right next to MIT in 2002 in a pretty remarkable move. So the CEO is Daniel Vitella. He had 6,000 scientists in Basel and very good jobs, very productive place, but they weren't developing new to the world medicines. He got a wild idea. I'm going to move all my research staff to Kendall Square. 6,000 Swiss were given a slip that said, move. Now, how many do you think moved? No, not in their comfy life in Switzerland. 100. Well, you guys are extremes. It actually was in between. 2,800 moved, okay? The others said, not going to America. Vasella was asked in the Financial Times, why are you doing this? And he gave a very quirky, fun response. He said, there's a great bar in Kendall Square called Stars and Plows. And if you walk by that bar at 7 or 7:30 at night, there's a bunch of people in white lab coats having a Guinness and racing out. And if you go back at 11 or 11:30, another group of people in white lab coats are there. And so the Financial Times goes, oh, Marshall, the secrets of industry are in the air. This is the story of economic agglomeration. Vasella goes further. He said, nope. I want them to be in that bar, and I want them to leave Novartis. I want them hired away. Now, why in the world would he go to the expense of moving 2,800 people, firing, sacking 3,200, moving them to Cambridge, Mass, to be hired away? What good would that do Novartis? Would create an ecosystem. The ecosystem's already there. Boston is the most productive place in the country. Might make him a hub. He wanted his people to be hired by other firms and universities. Why would he want that? So one idea is a very instrumental one. Ooh, they'll go away, but I'm not so sure how friendly they'll be. Hey, you drugged me from Basel to Boston, and now I leave? You want me to have ties back to you? Yes?
It creates an opening for someone else to be hired in?
It does more than that. You're on target. It creates a vacancy, but it also is a signal that the Novartis people were good enough to be hired away. All right? And so what he wanted to do, back to your create an ecosystem, was send a signal that Novartis is a good place to work. We have high quality people. They're going to leave. I'll be able to hire back. In fact, he was able to convince Harvard to let a scientist who'd never before been involved in commercial activity at the medical school to become director of research at Novartis, on the grounds that they will only look for new to the world medicines, not medicines for the marketplace. Not the idea of making Me Too's or making things that make money, but rather, can we go after uncured diseases? Can we go after new things? Suddenly, Novartis becomes big fish in town. Novartis' next move is to San Diego, where it partners with UCSD, the US NIH, to create the Novartis Nonprofit Research Institute. And so this idea that the transformation happens to commercial entities is an interesting one. All right, I gotta slow down. I'll tell too many stories, so we'll switch. All right, so we think we have a recipe. We rush off and do the same thing. Took a long time to do this back then to the Bay Area. Uh-oh, it's not the same. Here we thought Stanford and UCSF would be the center. It's not. It's two companies formed out of those universities, Chiron and Genentech, first-generation companies. Odd, strange companies in which the monkeys were running the zoo. They were run by academics, and they did peculiar things. They let their scientists publish. They collaborated with competitors. They had more ties to university scientists than they did to pharmaceutical companies. The connectors in the Bay Area were these first-generation companies and venture capitalists. And part of what VCs did was spread ideas across firms, okay? It became very important. They became the carriers in this process. So we began to realize it's not the ingredients, it's the cooking, okay? So depending on what the ingredients are, there are different recipes for successful cluster formation. The endowments in different places are quite different. Different organizations can be anchor tenants. In the Bay Area, it was this first-generation companies. It was also the active engagement of venture capitalists. But there was a relational model of technology transfer I can't go into now, but if you want to ask in the Q&A, developed here at Stanford that would catalyze relations with small firms. And there was this intense blending of public and private science between the two settings. So what you saw was a kind of topology of the possible. Okay, so we go down to San Diego, very sleepy Navy town that somehow became a high-tech city. North San Diego County became a center for biotech and a center for wireless technology. And how did it happen? Here I'll spend a moment telling the story because it's a fun one. There was a guy who was a postdoc here at Stanford, Ivor Royston, who had great aspirations. He came from Johns Hopkins, he came to Stanford. He said, I'm going to cure cancer. He gets a job at what was then a relatively new university, UCSD. And he takes his lab tech with him. He has a dream that he'll cure cancer, and that dream kind of fades over time. He realizes he's not a superstar, he's good. But what he thinks he can do is help develop the tools for the war on cancer. And so he develops these diagnostic tests based on monoclonal antibodies. All right? He tried to get funding for it. Everyone turned him down. The NIH said, not possible. You have to bleed pigs and you have to bleed cows to get the monoclonal antibodies. You can't make it in a lab. He goes to the pharmaceutical companies. They turn him down. He goes home one night. He's sitting at the kitchen table with his partner. And she says, what's wrong? You seem so depressed. My life's dream's going away. And she said, well, what do you need? He says, I need like $250,000 to do this, $250,000. She says, well, you know, there's something I never told you. When we were together at Stanford, I was also dating someone else. His name is Brooks Byers, and he's one of these venture capital guys. Do you want me to call him? To the guys in the room. How many of you would say yes? All right. Not that many hands went up. He says, okay. She calls him. No, she says, but look, I moved here with you. So got to keep that in mind. She calls him. Byers, Tom Perkins come down a week later. They meet with him. He shows them what they can do. And they say, okay, we're going to fund you. They travel to the airport together. He says, Three things. One, you need more than $250,000. We'll give you more. Second, I need to go see the chancellor and see if this is possible. So they visit the chancellor. This turns out to be immensely complicated. The faculty senate gets involved. He gets all kinds of arrows in the back. You end up having a faculty senate vote. It passes by only 2 votes. Same thing was true for Genentech's original founding. Academics thought this back then was heretical activity. Today they build a building in your honor, and Royston has such buildings at UCSD. But at the time he was a pariah. And they said, and third, Byers is going to move down here and be your CEO. So the ex-boyfriend moves to San Diego and runs the company for a brief period of time. The company is an unusual one in that they're not developing a drug, they're developing tools, okay? So it means they don't have to go through FDA approval. And they became the first company to actually go public, have a big IPO, and then get gobbled up by a pharmaceutical company. Eli Lilly bought them. Lilly jokes today they're the leading venture capitalist in the San Diego area because within 1 year, not a single hybrid tech employee worked for Lilly. They all took their money and run. They got 600,000 shares of Eli Lilly stock, and they took off, okay? Now, did they come to Napa Valley and buy wineries? Turns out no, almost every one of them. Well, let me back up. Why the mismatch with Lilly? Most of the hybrid tech employees were 28, 29-year-old women with PhDs in molecular biology from UCSD and Caltech. They were working for 58-year-old men with a BA in chemical engineering for Purdue. As they described it, it was like Animal House met the Waltons, or like working for your grandfather. So all these hybrid tech employees stayed in the San Diego area, but San Diego had no infrastructure, had no law, had no venture capital, nothing going on. But UCSD, Scripps, and Salk saw an opportunity, and they started to have Friday beer bashes on the beach. It was called Biotech Beer in the Beach. And they met every Friday and flew in experts from Silicon Valley, from Boston, from other places to try to teach people about how to start companies. And the young women who made all this money, and Ivor Royston, went on to create more than 40 biotech firms in the San Diego area. You've got money, you've got the beach, you've got a great climate, you have the intellectual life around there, and now that area that used to be a great surfing spot is now kind of biotech as far as the eye can see. So the failed merger actually fueled the San Diego cluster. All right, so if you look at the evolution of San Diego, in the bottom one you see increasingly the internal cohesion that's going on. All right, so real quickly, comparison of 3 success stories. Different organizations are the anchor tenants. I want you to think about, there's not a standard solution, there's a topology of the possible. In Boston, it was the public research organizations. Bay Area, it was tech transfer and venture capital. San Diego, it was the story that UCSD and the nonprofits played a role. In each case, lots of job mobility, people moving across settings, local competitors who collaborate, public and private science interwoven without the control of a powerful organization, okay? So a rich stew in which things happen. All right, so we built this database, and then good friend Ron Burt, University of Chicago, said, have you studied the ones that failed? And we're like, all right, let's see if we can do that. And it turned out that the most interesting thing is that all of the success stories are different, all of the failures are the same. All right, it's the reverse of Tolstoy on families. So let me run you through rapidly so we can have a few minutes for conversation at the end. Let's look at the places that failed. What you want to see is that there's lots of participants, but the activity in the middle doesn't take off. So the first one on the top is New York. It actually looks like a New York rivalry, stiff shoulders, you know, sharp elbows. It continues that way, and it continues. The number of players in biotech grow. There's some very well-connected players. Sloan Kettering is connected globally, but a cluster does not develop in New York. If we go to New Jersey, there's a cluster around the pharmaceutical companies. It keeps reshaping, but it never congeals in the overlapping way of the Bay Area. If we go to Philadelphia, it ends up as like a standoff. It's like a shootout at the OK Corral at the end. If we go to Washington, D.C., that brown node in the middle is the National Institute of Health. Red is Johns Hopkins. But it never catalyzes. It looks like, if we were betting at the early stage, Washington is a place to see it happen, but it doesn't take off. Research Triangle, nothing really grows. Houston, MD Anderson Hospital, nothing really grows. Seattle tries. If we had this today, you'd actually see a bit of a network. We've done some work. Christian Whittington and I have brought these data into the present. And Seattle's actually become a cluster around vaccines. And so part of the story is there, but the other side is there. In the cities where it doesn't take off, there's not an anchor tenant, but what we call an 800-pound gorilla. When we published the book, we got a quick email from a famous primatologist who said the largest gorilla is actually 534 pounds, but you know the point. An 800-pound gorilla says, play by my rules or leave. Okay, in the other places, New York, it's the finance industry. Washington, it's the government. Research Triangle, it's the universities. In Seattle, it's the Gates Foundation. These are anchor tenants who say, do it my way. And so the possibility of transposition is not there. So in all the places I could go on, you can see through periods, the same actor is the most powerful in the failed ones. But in the successful ones, the one who starts it passes the baton to someone else to carry the lead. They don't have to be in charge the whole way. Okay, so all of the regions had endowments, but only a few were places in which the anchor catalyzed further development. And you saw these cross-network transpositions. Biotech firms collaborated with other biotech firms. The scientists published in academic journals. Universities became, like Stanford, like MIT, and UCSD, incredibly active in the commercialization of knowledge. VCs became executives of companies. They became donors to universities. BioX here at Stanford was very much funded by some of the people who made money out of this. And serial founders of biotech firms, like Royston, become venture capitalists. So the clusters that become successful have high rates of foundings, and I want to call it disbandings, okay? Let me stress that. Atul Gawande, who's a great science writer, remarkable doctor. He writes for The New Yorker. This is back, I forget, maybe 10 years ago now. He read some of this work and said, I want to write up a story about it in The New Yorker. He calls me on a Sunday night and said, I'm sending it to you, read it and make sure what I've done is right. I read it, goes back to him, said, looks fine. He said, be prepared. I'm like, really? You know, academic research, people don't pay attention. So I'm in the office next day at 11 a.m. Sure enough, mayor's office, San Diego calls. Professor Powell, yes. We really like the story on San Diego, but you say we have the highest rate of failure in the country. And I said, no, I said you have the highest rate of disbandings. Well, that's not good, right? And I said, you have the highest rate of foundings and disbandings. That's actually really good. How is that possible? And I'm like, snotty academic, do you read Darwin? I mean, you know, it's sort of, you've got the bar so high in San Diego that you have to be really good to survive in San Diego, okay? And if we want to start a company in Atlanta, no problem, we don't have to be that good. But in San Diego, you know, the rate of success, these are all companies that are swimming in the fast lane in the swimming pool. She says, will you explain that to the mayor? They're really upset. So finally I go down and talk to some people in the San Diego office. I was totally blown away. They're like, look, this is great for biotech and it's great for software, but how do we get this not just at UCSD, but at San Diego State and into the high schools? And they hit upon a fantastic idea to move biotech into beer. And that's where White Labs is. It develops strains of yeast for microbreweries. You know, they're very busy trying to think how not to have only jobs for PhDs, but how do we get jobs for people with high school degrees and 2-year degrees. And so what you see in successful clusters is high rates of people bumping into one another, changing ideas, mixing and trying different things. In unsuccessful clusters, you have people saying, do it my way or get out of here. So most people think about networks in terms of brokerage. I have an idea, I charge a toll or rent for getting to others. We want to think about not what are called structural holes, but folds. That is the connections in which people link different ideas to one another. I should stop there. I won't go through all this different stuff for a conclusion, but thank you.